Okay, welcome. I don't know. I think there is an issue with my audio. Yep, there is. Anyway, you still hear me, guys, can't you?
Yes.
Yes.
I didn't hear anything. Are you still okay? Can you hear me or not?
Yes.
Okay, very good. There were some issues in here with my audio, the way it was set up. Anyway, let me get into the PowerPoint. You guys have a quiz today, okay? So after the class, you can start taking the quiz. That covers basically the chapters, the 3 chapters so far, basically chapter 2, 3, and 4, or chapter 1. So these are the chapters, the 4th chapter right now that we're in. Let me go back into to this one in here and start sharing my screen. So this is about chapter 4, namely Newton's second law of motion, okay? Any questions before I basically delve into the topic? No? Again, there was some changes. Apparently, I didn't know that there were issues, and now I learned that it was an issue from another class, actually, with the Confer Zoom. I think sometimes what it does is it breaks down the recording into several portions. So what that student happened to him is basically he didn't know which one is first, which one is second. So I went there, and sure enough, they were actually there is like a timestamp on them, namely the date, the time, and all of that. So that's how you can find that which one comes first, which one comes second. But what I did, actually, I removed them altogether from there because of this confusion. And there should not be any recordings in there. Rather than that, what we have is what we've been doing, namely the fact that all of the recordings are going into the you know, every chapter has a discussion session below it. I know it has the terms, it has also the PowerPoint, basically the notes from the class and so on and so forth, but there is actually a discussion session in it. In the discussion session, I basically upload the same video, and if it's broken, sometimes it's actually broken when the session becomes too long. I don't know if it happens with your class. I don't think it did, but at least if it did, what I do is I combine everything into one recording, upload it to YouTube, and post the link in there so that you guys find it in there. So if you're used to going into Confer Zoom to find the recordings, you really shouldn't be doing that. Go straight to the discussion, because then while you're watching the video, you could take notes and answer the discussion session right there and there. So it has a big benefit of doing it this way rather than of how some people probably have been used to, because probably from other classes where the instructor doesn't give them the link, they assume that the link is in Confer Zoom. I don't do that, because every lesson has its own discussion. That's where the link is, and that's also where the discussion and everything, the assignment is, and everything else. Does this make sense to you guys?
Yes.
Okay, very good. Also, it would help you actually if you subscribe to the YouTube channel. That way, if a video is uploaded, you don't wait for me to actually upload it and then for you to go and look at it, because sometimes it takes a long time, and especially for late classes, I tend to do it in the morning after, when I actually go and post it to you guys, because it takes a long time for, first of all, the upload, second is Google does its own things to index videos and do all kinds of things. So if you're a subscriber to the channel and you notice that there's a notification that came in that there is a new upload, obviously, since I have a lot of classes, you're looking for the class for you that starts with the PHY10, so you know it's your class. Okay? If you see something else, PHY4B or some 4C or something else, just skip that if you don't want to basically be bothered with it. But that's basically because I put them all in the same YouTube channel. So that's in terms of working together. Today's chapter is all about Newton's laws of motion, basically the second law, which is really, I mean, if you want to call it, this is the law. This is the most important law of Newton's laws of motion. This law carries with it a causality effect. There is a cause and effect in it, okay? The effect is a change in motion, and the cause is a force. So there is a cause and effect in it. So what causes acceleration? It's a force. So there is a causality in here. There is one thing comes first, which is a force, and the result of that is a change in motion, namely acceleration. So this is a change in motion. What I mean by change in motion is change in velocity motion, okay? And this change can happen in one of two ways. Either the velocity, the magnitude of the velocity changes. Case in point, you were going 50 miles per hour. And now, for example, you're going 55 miles per hour. So your speed has definitely changed in this case. So there must be a force that caused that, okay? Or you could have maintained your speed, put your car on cruise control, for example, at 50 miles per hour, but go on a curve, turn one way or the other. Then in this situation, also a force must have caused that. In either case, a force causes change in motion, whether in magnitude or in direction, in general, in both. In general, both these two quantities do change. So that is basically what this law is talking about, okay? So this law is telling you how this force causes a change in motion, okay? And the motion in general, like I said, meant with it the speed. I mean, velocity. Speed is just one aspect of it. Then we're going to talk about the force of friction, which is really a force due to the contact between two objects, basically, because their outer layers, especially their electrons at the end, they interact with one another, okay? If you touch something, the only reason why you feel it actually is because of the electrons that are in your skin touching the other material, interacting with the electrons in the other material, and that's how we feel things. That's how we touch things, and that's where friction is. So in this case, this interaction yields the friction. The phenomenon of friction is associated with almost any mechanical motion anywhere, okay? So it's sometimes it's a problem, and sometimes it's actually a plus. Without friction, we cannot move. Without friction, your car cannot go anywhere. That's basically the bottom line. Because, case in point, for example, if you are on an icy day where there is a little friction, your car can spin in its place forever and ever. It will not go anywhere. So it's really what causes car to move is friction, really. But sometimes it's an undesirable thing, okay? It's the same friction that causes wear on your engine. So it's not good. So sometimes it's something that you want, and sometimes it's something that you don't want. So that is basically in a nutshell what friction is, okay? We're going to talk about the concepts of mass and weight. Sometimes we confuse the two with one another, especially in the American system. We use pound for both of them, okay? For the weight, we say something weighs 5 pounds, and how much it is, it's 5 pounds. But in physics, and actually even in the American system, there are two kinds of measurements for the pound in this case. It could measure the quantity of matter, which is mass, or its resistance to the change in motion, which is called inertia. And in the same time, there is something else, which is the weight. The weight is actually a force. This is a force. Whereas this one is a positive scalar. It's a positive number, like 5 or 7 or 8. It can never be negative. You cannot have a negative 5 pounds. That doesn't mean anything, okay? So mass is always positive. That's basically, it's a quantity. It expresses the amount of something in terms of its content, what's inside of it, okay? Not necessarily the space it occupies. That's the volume, okay? That is something else. But how much stuff is inside that object, or more physically appropriate, it's the resistance to the change in motion. Remember, this cause and effect relationship in here, force results in an acceleration. It's not exactly equal to objects with bigger mass will resist less or will resist more to the change in motion. In other words, it's very hard, for example, for me to try to push the train into motion, but it's very easy for me to do the same thing for a bicycle. I can, if all I can do is, let's say, for example, 10 pounds, 10 newtons, then in this case, probably the 10 newtons will do an effect on a bicycle because it has less inertia than on a train, okay? So in this case, if the train was stationary, it's very hard for me to produce a change in motion for the train using the 10 newtons with my own hand. Whereas it's probably a lot easier for me to do the same thing for a bicycle because it has less inertia, less resistance to the change in motion. The same thing, if the train was coming at me and I decide to stop it with 10 newtons, it's going to be very hard to stop it with my 10 newtons because it has tremendous inertia. So it's going to zoom by, probably cause a lot of damage in the way. And I probably will not be here to tell you about it, but that's another story. And the bicycle, on the other hand, it's probably easier for me to stop it with the same 10 newtons, at least relatively speaking, depending on how fast it's moving, but I will have far better chance with the bicycle because it has less inertia, less mass, okay? So actually the quantity that fixes this relationship is the mass. In other words, the change in motion is inversely proportional to the mass. The bigger the mass, the less the change in motion, okay? So that is basically what the second law is. As a matter of fact, this is the second law of Newton, okay? In its glory, okay? We call it a law because of the fact that every observation that we do in nature supports that. So what we do in this case, we go in the laboratory and we measure the acceleration and change in motion. It doesn't matter with the bicycle, for example, okay? And we know how much force we have applied because we can attach to a spring and basically see how much the spring, for example, is compressed or elongated, depending on which way you put it. Then we can find the force in Newton, and also we can measure the mass of the bicycle independently. Actually, using another system, we can weigh it, but that's true only on Earth. But we can use actually a spring also to find the good definition for the mass and measure it. And then when we put them together, if this number, let's say, for example, is 2, and this was 10, and this is 5, then it's always true in this case, because 10 over 5 is 2. That's what a law means, that whenever we measure these things independently, we always find this relationship true. So it throws from some sort of a hypothesis to a level of becoming a true thing. So because it happened in the past with a lot of experiment, and it's happening now with experiment, we expect it to be true also tomorrow and the day after, and so on and so forth. So that is the second law of Newton. And as I was saying, this is probably the most famous law that you're going to know about. If anybody asks you, what did you learn in physics 10? You tell them, I learned about the second law of Newton, F equals to ma. This is basically the law, okay? As a matter of fact, this is the law with a capital T. Okay, so
what was the formula again?
It's F equals to ma.
Thank you.
But usually it's written in this format to express the cause and effect relationship between the two. Because you want an A, how would you get an A? Through a force F. F gives you an A. Of course, the annoying parameter in here is the mass that basically attenuates this expression, basically diminishes it's depending on how much mass you have. It's much easier for me to push a mouse, for example, versus an elephant. An elephant has more mass, therefore it's harder to push than a mouse in this case. That's what that M is standing in there for. Otherwise, if you apply force on a mouse and a force on an elephant, you're going to produce an acceleration. That's how it's written normally, okay? So this is the law.
Okay.
Okay, very good.
So F is a force, M is mass, and A is acceleration, right?
Acceleration or the change in motion. Okay,
Okay.
that's exactly the
Thank
same
you.
thing. The only thing in here, we're going to get into the details. The change in motion can happen in one of two ways, either in magnitude or direction, because velocity or motion is a vector, meaning that it can change one of the two quantities, because a vector has magnitude and also has direction. So if you want to change motion, you can change the magnitude. Let's say, for example, you were doing 50 miles per hour and now you're doing 55. You have changed the magnitude in this case. And you stayed in the same straight line. You didn't turn or anything like that. So in this case, the velocity has changed, the motion has changed. Something must have caused it. Or you maintain your 50 miles if you like, but go on a curve. It's the same thing in this case. You changed direction. So in this case also, something must have caused it. Okay, so that is basically in a nutshell what this chapter is about. We're going to talk about the free fall. Free fall is basically when objects fall with the acceleration g on Earth. That is basically a free fall. When an object doesn't fall with the acceleration g on the Earth, for example, there is an air resistance, slows it down, then in this case, it's a non-free fall. But this is basically what this chapter is all about. If you're good with this one, we're done. No? Okay, as I was saying, this is the law. This is probably the most important thing that you're going to learn from this class. So I hope you guys, if a police officer stops you tomorrow and tells you that you're in violation of the law, tell him in which way, because I know the law and I don't think that I'm in violation of it, because if it is, then we have to change this law. Okay? You can argue with him or her. Good? What do you think the police officer will tell you if you tell him that? Are you going to be happy with it?
I don't think he'd understand.
Okay, so acceleration is directly proportional to the net force. To increase the acceleration of an object, increase the net force acting on it. So the acceleration and the net force basically are proportional. That's what that means, okay? That's what I was writing earlier. This symbol in here is for proportionality. That means proportionality with A. Usually, if you want to have A higher, just get a higher force. If you want to have an A less, just get a less force. If you want to have no A at all, if you want A to be 0, you can just put F equals to 0. If there is no force, there is no acceleration. Actually, you're back to first law of Newton. Okay, that's why this is important, because it actually encompasses to some extent the first law of Newton. Okay, so this is really an extension of the first law. Okay, the problem usually is not, honestly, when we're dealing with this law, it's not this law itself per se, it's this force F. I mean, modern physics now deals basically with F, trying to find these forces. So we have to really have a full account what these forces are. And the forces in nature, they boil down to one of four, okay? There is a so-called gravitational force, gravity, which we're going to be exploring today in all of mechanics. And that is basically due to masses, okay? Mass has a gravity, it has mass, and it's going to attract another mass and so on and so forth. On Earth, it's Earth, actually, okay? That's one force. The second force of interest to us, and I'm going to leave it last, is a force of electromagnetic force, okay? Let me talk about the other two forces first. The other two forces are the nuclear forces, and they are strong nuclear force that holds the nucleus together, and the weak nuclear force that is responsible for radioactivity and other phenomena. The strongest force ever is a strong nuclear force. That is by far. It holds basically the proton and the proton, and the proton and neutron and neutron and neutron inside the nucleus. That is the strongest force. That we don't really see it on a daily basis because of the fact that we are living basically, I mean, most of the time, atoms exhibit themselves through electrons. So most of the times we deal with the electrons, which brings me to the second force, which is the electrostatic force, electricity and magnetism force. That one is the one that is responsible for most of the forces other than gravity that we deal with on a daily basis. And this includes friction. Friction is one of them. It's the interaction of charges. push and pull is actually an electrostatic force. The spring constant force is in its essence is actually an electrostatic force, electricity and magnetism. So that's something that we're going to discover later on. But at this point, this is the breakdown of them. But from a mechanical point of view, friction appears to be one of the other forces that we deal with on a regular basis. And this is how the interpretation for it is. So at least the macroscopic, the big picture, not the microscopic. Microscopic, we know it's electricity. And we're going to get into it down the road. But macroscopically, from the big picture, what I see in here, I see two surfaces in contact with one another. And when one of them slides on the other, I see that there is a friction. As a matter of fact, I can feel it by heat. You can do it yourself. And you can see that your hand starts to warm up. Where is that energy coming from? It's coming from this rubbing in here. And that's how the increase in temperature is. So when two surfaces are in contact with one another, they produce this kind of force, which is called the friction. Okay. Friction on a microscopic level is exactly what I was talking about, is this interaction and these grooves in here that tend to be, at least mechanically, they tend to be stuck into one another. And basically, there is like a release point before the next one and so on and so forth, okay? Friction appears in several shapes, even in mechanics, okay? There is one of them we're going to discover later. There are two kinds of frictions in here. There is a static friction, like the one, for example, right now. I'm pushing on the desk. The desk is not going anywhere. Since I am pushing on the desk, I have put F on the desk. I am pushing with a force F on the desk. Here is the desk. I am pushing it. I don't know how much I pushed, but it's probably not much right now. Let's say, for example, for the sake of argument, it's 10 Newton. But the desk is not moving. Remember, I just said that if I apply a force 10 Newton, for example, on the desk, whose mass, I don't know, let's say with this computer and stuff on it, let's say, for example, it's 50 kilograms. I should see an acceleration, which is simply 50 over 10, 10 over 50, which is 0.2 meter per second per second. But this desk is not moving. So the acceleration is 0 after I pushed it with 10 Newton. So something prevented it from moving, and that is friction. And that friction, the desk is in contact with the surface in here, and it's being pushed back by the surface due to friction. If I'm pushing it this way, the friction will push against me. As a matter of fact, if I go to the other side to help the friction, because the friction is pushing this way when I push this way, the friction will change its mind and push in the opposite direction. It's always pushing in opposite to where I push, okay? So in this case, I have the 10 Newton I'm pushing with. Friction is pushing in the opposite side by another 10 Newton, and it's exactly what the doctor ordered to maintain the desk in place and not move, okay? So if I decide, you know what, I don't want to push with 10, I want to just push with 5, friction will change also from 10 to 5. So if I lower, if I don't push at all, right now I'm not pushing, friction stops from pushing. So the friction in this case, the static friction, where the desk is not moving, it's variable. If I put, let's say, for example, 20 Newtons, friction will put 20 Newton to keep the desk from moving. And the friction is in the contact basically between the desk legs, that has 4 legs, and the surface underneath, okay? But if this desk starts to move, if I push very hard and the desk starts to move, it doesn't mean that the friction is gone. Now the desk is moving, and I am applying a force to it, and that type of friction is not static anymore, it's kinetic friction. So there are 2 types at least of mechanical frictions that we can identify. One of them is static and the other one is kinetic. There is another friction that we're going to discover very shortly. It's the drag. And that is when a parachute comes down in the air, or any object moving in a fluid like the air will experience drag. Like, for example, the airplane taking off and things like that. That is actually another kind of friction too, because the blades of the helicopter or the drone or the parachute, for example, surface, as it's in contact with the air, that actually also is friction. But its properties are different than these 2 types of frictions that I have described in here. There is another friction also that is familiar to all of us, is viscosity. If you take, for example, water and you pour it, for example, from a cup of coffee, from a cup of whatever, you will see that it's flowing. However, if you take oil, it's going to come at a different rate. If you take the 2 and pour them next to one another, one of them would flow faster than the other. One of them has higher viscosity than the other. As a matter of fact, if you're going to change your oil on your car, the oil that you're going to change with has different values for the viscosity, and depending on the weight of the oil, that actually is determined by the number that determines actually the viscosity. How much do you really want the fluid to move when the pieces inside the engine start to warm up? Okay, because you would want to absorb that heat that is coming from the friction of the moving parts inside the engine. So you send the fluid there, that fluid warms up and takes that heat with it and basically pushes it away so that there is no breakdown, no mechanical breakdown due to this friction. If you don't have oil, these things start to rub against one another, and because of the heating, they start to warm up until they fuse or they destroy one another. So you have to have the oil there, and the oil has specific weight that is determined by its viscosity. As a matter of fact, if you take honey, for example, and put it next to water, you know honey has a very high viscosity in this case. That is actually friction too. So all of these things are friction. So this is the type of force that we need to understand. Obviously, for moving objects, the two frictions that I mentioned will be first, namely the kinetic friction and the static friction, will be enough, at least in the beginning. But toward the end of this chapter, we're going to be talking about the drag force, which is another kind of friction, okay? The force of friction can occur with the sliding objects, in water, in air, or all of the above. What do you guys think the correct answer to this question is?
All the above.
All the above.
Yeah, I just mentioned several examples for you guys that with the disk it happens, with the oil it happened, with the air it happens, so friction is everywhere, okay? As a matter of fact, friction has a name in physics. This is what physicists call it. That's how they call it. Samantha, you're upside down. Are you okay?
Yeah, I'm okay, thank you. Just how I wanted my picture.
Okay, no problem. Okay, so friction is the bad boy of physics because every time, I mean, the problems will be very, very nice, okay? Your equations, your F equals to ma, all of the things will be beautiful. And you come up with the immaculate equations, but you know that they're missing something more realistic because of friction. But the minute you plug in friction, things go south on you. First of all, the direction of the friction, you have to be very careful with it. Sometimes you come up with an answer and it's completely nonsense. So you have to go back and redo the whole calculation all over again because you took the wrong side of the friction direction. And you cannot tell until you actually find the solution. So it's really, there is a guess game when it comes to friction. And that's why physicists don't like it very much because of this, because of its properties, okay? But again, deep down, it's actually electrostatic force, but acting on a statistical, how should I say it, very, very large number of them. If it is one electron by itself, yes, but there are so many of them. There is an Avogadro number of them, which is then makes it very hard to really predict them on an individual basis. So you use what is known as statistics, mechanical statistics, then to describe the behavior if you ever are going to really deal with it. It's a nightmare in terms of calculations, okay? But as I said in the beginning, friction is sometimes something positive. You really want it in the system to work with it, and sometimes you don't want it because it's an undesirable effect, okay? For example, if you saw ever any space movies, there is no friction in space when you are in space. How are you going to walk back to the station? How are you going to come back to where you started from? You left the station, you want to do some repairs outside of your ship, and now you want to come back. You cannot walk back because there is no friction. You are suspended in the middle of nowhere. So in this case, use actually the third law of Newton, which is the action-reaction. Fire something one direction and hope to end up in the opposite direction. So that's the other solution for you. And that is something later on we'll see, the conservation of momentum, okay? Send something one way and you yourself, you're gonna move in the opposite direction. So again, yes, you're right, all of the above. When Sanjay pushes a refrigerator across a kitchen floor at constant speed, the force of friction between the refrigerator and the floor is... Now, here is the deal. This is kinetic because it's moving, okay? So this object is moving at constant speed. When it's constant speed, that means A is 0, correct? Because the motion is not changing. That's basically, and A is a measure of how much the motion is changing. So in this case, the forces acting on the refrigerator are 0, because the refrigerator is moving. Sorry? Yeah, so now if he's pushing with a force, let's say, for example, 10 Newton, the friction in the bottom must be also 10 Newton so that they cancel one another and the refrigerator does not gain or lose speed. Okay? Then the correct answer is C. Is that what you said, Brandon? Or somebody else? Yes?
Excuse me?
Is that what you said, C?
C, I said C.
Yeah, that's correct, okay? Because the acceleration is 0, so some of the forces must be 0 in order to maintain its speed. So this is a type of kinetic friction. Why it's kinetic friction? It's because it's moving. This one is. I mean, the guy has to push for the refrigerator to move. If you don't push it, the refrigerator will stay in its place. So when Sanjay now pushes the refrigerator across the kitchen floor at an increasing speed, the amount of friction between the refrigerator, now here is a problem. A is positive because it's increasing now. The refrigerator is gaining more and more speed, okay? So now let's say, for example, he's pushing with a force of 10 Newton. This cannot be 10 Newton anymore, because if it's 10 Newton, they cancel one another, and then I will have MA. A is not 0, but positive number. This is mass of the refrigerator, by the way. So this 10 must be greater than this one. So if this one is 8, that's fine. 8 Newton subtracted from 10, that's going to be a positive number. So no matter what in this case, it's going to be less than Sanjay's push. The friction has to yield a little now, okay? Otherwise, it's not going to work. Mass, the quantity of matter in object. So that's basically how we define it. It is also the measure of the inertia or sluggishness that an object exhibits in response to an effort made to start it, stop it, or change its state of motion. Weight usually is the force upon an object due to gravity. So weight is a force. Weight is measured in Newton. This one is measured in kilogram. This tells me the amount of stuff, okay? So there was a convention. People took this material and put it in the museum in Paris, and they said, okay, this is 1 kilogram. And from that point on, that is basically the standard for measuring mass, because it's really confusion. I mean, let's say, for example, when I buy some amount of, I don't know, whatever a commodity I want to buy, and if there is no standard in here with which we weigh things, there will be a big problem, okay? Social problems, economic problems, and so on and so forth. So that's the agreement on it, and it's actually used also in physics too as the standard for measuring masses. The fact that we agreed on a certain amount does not make it wrong or right. It's just basically an agreement. It's like, for example, this ruler, having decided on a certain length to be a standard length, and that's it. Instead of deciding, for example, on somebody's arm or how many feet there is, because some people's feet are more than other people, so which is really which is subjective. Then we decided on something and said this is the unit for measuring masses. And it's really, as I was explaining to begin with, is really the how much an object objects on its change in motion. Okay, if it was at rest, it wants to stay at rest. It's harder to move an elephant than a mouse. But if the elephant was moving and the mouse was moving, it's actually easier to stop the mouse than it is to stop the elephant. In the same token, because of the fact that the elephant still has more inertia in either case. Okay, so that's what we call the inertia of the object. Okay, so mass and the word inertia are interchangeable. Okay. So again, a measure of the inertia of the object independent of gravity. So this is true all the time, and it's greater. So independent of gravity, greater inertia, greater mass. The same thing actually. Unit of measurements is in kilogram, whereas weight is usually the force of an object due to gravity, and the unit for it is in Newton. And in also we use pound for it. Okay. So if, for example, you have a mass of, let's say, for example, 100 kilograms, which is big, okay? I hope that it's too much of a mass. Let's say, for example, more realistic number, 70 kilograms. So if you weigh, if you have a mass of 70 kilograms, then your weight on Earth is 70 times 10, which is 700 in newtons, okay? Your weight on Mars is going to be less. It's going to be what, about 2/3 of this amount, okay? And actually slightly more, and the weight on the moon is going to be less than that of Mars, and so on and so forth. If you are on Venus, you're going to be weighing a little over 650 Newton, but your mass never changes; it stays the same. It's always the same. Okay, if you are on the surface, not on the surface, on upper atmosphere of Jupiter, you're going to weigh about 2.5 times as much. So you're going to be about what, 1,800, maybe 1,700 Newton. But try to survive the atmosphere of Jupiter. That's another problem. Anyway, so this is different. This is a force. The weight is a force. Like any other force, like the friction, for example, okay? And this is a number. This is a positive number, which is the inertia or the resistance to the change in motion. They go together now. The weight actually has this expression in it, is equal to mg. On Earth, g is 10 meter per second squared. So if the mass is doubled, the weight is doubled. If the mass is halved, the weight is halved, because this number doesn't change, okay? It's the same thing. Mass and weight in everyday conversation are interchangeable. Mass, however, is different and more fundamental than weight, okay? So because sometimes it's kind of confusing, especially since we use the scale on Earth, and you go to a store and tell them I need, for example, sugar or flour, and they tell you how much do you need, and even if you're using the metric system, I'll tell him I need, let's say, for example, 1 kilogram of flour. So what that person does is takes the scale and use the scale to weigh 1 kilogram. So this is the kilogram, and puts the flour in here and gives you what is it? 1 kilogram worth of weight. Okay, so this is 1 kilogram times g. This is the amount of flour times g, and you cancel g from both sides and tells you, okay, I gave you 1 kilogram worth of flour. Okay, do you understand the problem in here? So even the process through which we do stuff on Earth is using the weight. Okay, that's really how, and you can still do the experiment on the moon if you like. Okay, if somebody was sitting on the moon, has a store in the moon, and you go and buy flour from them in the moon, they're going to do the same thing, except their value of g is slightly different, but it's going to cancel anyway. So it's going to be the same thing. Try to do this experiment though in vacuum. Try to do this experiment in space. It's not going to work, because you cannot, everything weighs the same in space because there is no acceleration in interstellar space. So you have to come up with a different technique to find masses. And usually use the acceleration, spin this thing a little and see how much you're going to get out of it of force. Then you're going to find the the mass, okay? The problem is, again, because especially in the American system where or the standard system, we use the pound for both of them, and that even leads to more confusion, okay? Mass versus weight on the moon and Earth. Weight of an object on the moon is less than that on the Earth, but the mass on both places is the same. It doesn't change, okay? The conversion between the kilogram and the pound is basically 1 pound is about 0.445 Newton kilogram or 4.45 Newton just by multiplying by 10, okay? Or 1 kilogram is slightly over 2 pounds. Okay, we saw this one when we did the last time. Did we just see this one or not? Yes, I think we did.
No.
We didn't see this experiment? Oh man, then I'm getting
No.
confused. We didn't do the inertia last time, the experiment with the, let me see here. Do I have a pen in here? This cup. I'm getting old now, okay? I don't remember what I've been doing in here. Okay. Maybe I use it on this surface in here. Quickly.
Was it the experiment with the cup, coin, and the flick of the paper?
Yes.
Oh, yeah, then we did do that experiment.
So that's the same thing. The idea of the inertia is the same thing in here. And that is basically, we demonstrated the concept of inertia via that experiment, okay? Okay. So again, this we saw the acceleration is inversely proportional to the mass or the inertia. And this is the example I was giving earlier with the bigger mass having higher. You need a lot of force to produce the same acceleration for a bigger mass than it is for a smaller mass. And this is the second law of Newton. This is basically the item. I want you to put it in your own words. Please do not copy and paste, okay? This is basically in a nutshell what this is saying, okay? If an object is under net forces, that will result in an acceleration that is inversely proportional to the mass and proportional to the force. So the change in motion is directly proportional to the net forces and indirectly to its inertia. I want you to really be familiar with this law because this is a big deal, like I said. This is the mathematical expression for it, but that's really the more or less the verbiage for it. You can write a lot of paragraphs just to describe this law, okay? I just basically put it briefly there, but this is basically what the second law is in this case. Preferably if you give examples on how it is applied. What does it mean when you change the force? When you double the force, the acceleration doubles. When you double the mass, the acceleration goes down and vice versa, okay? This is the item for the discussion today. Everybody good? Yes?
Yeah, I'm good.
Okay, very good. So again, this is the formula for it. You can write A equals to F over M, okay? This is the same thing. This is basically doubling the mass now will result in half the acceleration. Tripling the mass will result in a third of the acceleration. That's the same thing in here, okay? Because you put 2 bricks in here, all of a sudden, if it was accelerating, let's say, for example, with, I don't know, let's say 6 meters per second, now it's going to be going by half that much, 3 meters per second. If you triple the blocks now, you have 2 more, then in this case, again, you're going to drop it by another factor, which is instead of 6 divided by 3, it ends up being 2 meters per second, or 2 meters per second squared, okay? That expresses this relationship, really, 1 over mass in here. Okay, this is again the same ideas in here for all of these questions. Hopefully you guys, the free fall again, Okay, why is this here? So again, the greater the mass of the object, the greater its force of attraction. So that again, G is the same. So if you double the mass, you have twice as much weight over twice as much mass, and the two cancels and G is the same. All object will fall with the same acceleration. That is a free fall. So if an object is accelerating on Earth, toward the Earth, on with the acceleration G, which is 10 meter per second, or 10 meter per second squared, that object is in a free fall. Basically, that's in a nutshell what it means, okay? At one instant, what is the question? At one instant, an object in free fall has a speed of 40 meter per second. Its speed later. Remember, every second it gains another 10 meter per second. It's already going 40 meter per second. Now, a second later, 1 second later, you add to it another 10 meter per second because it's gaining 10 meter per second for every second. So its speed now is clearly going to be 50 meter per second. So that's what the free fall means. I know the word is used sometimes in the stock market. The stock market is on free fall, but that doesn't mean anything, okay? It's not falling at the rate of 10 meter per second, okay? They sometimes borrow stuff from physics without really putting numbers on them. A 5 kilogram iron ball and a 10 kilogram air ball are dropped from rest. For negligible air resistance, the acceleration of the heavier ball will be the same, because a 5 kilogram will be weighing 50 newtons, because 50 times 10 is basically 5 times 10 is 50 newton. And when you divide it by its mass of 5 kilogram, again, kilogram, you're going to end up with, sorry, by 5 kilogram, yes, you're going to end up with 10 meter per second. Whereas a 10 kilogram will weigh 100 newton. When you divide it again by its mass of 10 kilogram, the 10 kilogram will cancel. 100 divided by 10 is still 10. So both of them will end up with the same acceleration because both of them are in free fall. Their acceleration is the same. Okay, a 5 kilogram ball and a 10 kilogram ball are dropped from rest. When the free falling 5 kilogram ball reaches a speed of 10 meters per second, the speed of the free falling 10 kilogram is going to be also 10 meters per second. Because the acceleration is the same. Doesn't matter how big the object is or how small it is. Doesn't matter how much mass it is. It doesn't matter how much, because the forces will just double with doubling the mass. And since the ratio of the force over the mass is the same, G, so in this case, they will accelerate the same, okay? So now when an object falls downward through the air, it experiences, of course, the force of gravity downward, but also the drag force. So when I was talking about, this is another friction. And that is due to the air. If you do this experiment in vacuum, you're going 10 meters per second because there is no drag force. But because of the air, now it slows it down a little. Because of the friction, it's touching. The object is touching the air, and the air slows it down, okay? If you take the same object and drop it, for example, in a thicker air, there is more drag in there. So the density of the air plays a role in this case. If you put a bigger surface in here for the object, like for example, a feather, is going to even have more drag on it. So the drag plays a role with the shape and also the density of the air too, okay? Namely the temperature, because the temperature is influenced by the density. So that's in a nutshell what the drag is and how fast the object is. Because if the object is really not falling, there is no drag on it because it has to fall first to have a drag. If it doesn't have force, if it's not falling, it's not speeding up, it's not going to experience drag. So that is really the concept of the drag. So on Thursday last week, when the Mars lander basically was landing on Mars, it also took advantage of this by deploying a parachute and uses the drag force to slow it down. It was moving super fast and it was coming down with less speed. And at some point that speed was still too high. So they had to get rid of the parachute and basically deploy the crane there, which was using actually force in there, pushing on the air basically with those engines to slow it further down actually until it fell right in its place. So the drag force exists wherever there is medium, albeit on Mars is a lot less than that of the Earth because of the density of the air on Mars is a lot less dense than the atmosphere on Earth. Okay. So, and that is actually non-free fall because now we have a drag. The acceleration is not g. That's what non-free. The acceleration, not g. That is basically what, in a nutshell, non-free fall. Okay. So the condition for it is that the air resistance needs to be non-negligible, bigger parameter, and depends on two things: on the speed and the frontal surface of the object. Okay. It doesn't mention the density in here, but it plays a role too. But because the density is the same on Earth. But if you're going to do this experiment, for example, on Mars, there is a lot less density. Now it's going to impact the drag force, okay, the non-free fall. We're going to do this experiment on Venus. There is more air, actually. The air is far more denser in Venus than on Earth. So then there is actually far more drag on Venus than on both planets, okay? But on Earth, it's true, only on the speed and the surface. So if you want to achieve a drag force on Earth, just use a parachute as wide as possible, and you're in good shape, okay? Now here is the trouble with the situation. I'm going to explain it so the object starts, let's say, for example, we drop an object from the airplane. At this point, and let's say, for example, it has a surface. It doesn't matter, the surface at this point. It has no velocity when you immediately drop. So the initial velocity is 0. And so there is no drag. So at this point, all of its weight is pulling it down now. But then it starts gaining speed. So at some point, now it has speed. So the weight is still the same. It did not change. So if it was 100 Newton, it's 100 Newton. If it was 1,000 Newton, it's 1,000 Newton. But the drag force starts to build little by little. So initially, the acceleration is g. But now the acceleration is the difference between these two quantities. See, the acceleration is less than g. I mean, the acceleration is less than g. So it's going to still gain speed, but not as much as it did in the beginning. In the beginning, it gains a lot. But then, because the acceleration starts to be less and less now, because there is a buildup of drag force in the opposite direction, slowing it down. So in other words, it's not going to gain as much as it did in the beginning. And this drag force continues to increase until at some point it's going to be exactly equal to the weight. So the object will be moving super fast at that point, so that the weight mg is canceled by the drag force exactly equal. So at that point, the acceleration is exactly 0 because again, mg minus r is equal to 0, and that is, and that is equal to ma, and a must be 0 in this case to make up for this. There is no more gain in speed. You gain speed throughout the entire process up until this point. You cannot gain any speed anymore. You're going to reach the ground with that last speed. So this is called actually the terminal velocity. So the terminal velocity is the velocity with which you're going to hit the ground, or the object is going to hit the ground. And that is, it's going to gain more and more. In doing so, it's going to build up more and more drag until the drag cancels the weight, in which case you cannot gain any more speed. You have reached the terminal velocity at that point. Obviously, a more massive object, a bigger object, will have more weight and will take longer time to build up that terminal speed. It's going to fall with the same g initially, so both of them will have the same acceleration. So both of them, after 1 second, they will have 10 meters per second. But this one will need to build more time for it to come up with a drag force that compensates for its larger weight, for its bigger weight. So this one will hit the ground with bigger terminal velocity, bigger than a smaller object. Okay? It will take longer also to build up on its terminal velocity, okay? Because it needs more time to build up its terminal velocity. So which one will impact the ground with higher impact, the smaller object or the bigger object?
The bigger one.
The
The
bigger.
bigger one, because it has a bigger terminal velocity. It needs more time to build its terminal velocity. So for example, if this one at the end reaches the ground, let's say, for example, with 50 meters per second, this one probably will reach the ground with 70 meters per second. Okay. Plus this one is have more mass anyway. So let's say, for example, this one has, for the sake of argument, 70 kilograms, and this one was 50 kilograms. So you're looking at 50 times 50, a momentum of 50 times 50, which is 2,500 kilogram meter per second. Whereas this one, 70 times 70, which is 4,900 kilogram meter per second. This definitely will have a higher momentum. So when it hits the ground, it will have a higher impulse too. Bang. Because that's the change in momentum from 4,900 kilogram meter per second down to 0. Whereas the other one is only 2,500. So it's almost double in this case, okay? You double the value. So it's a big deal, okay? So that is the second item of the discussion today is the more massive object, the bigger the terminal velocity, okay? If everything is equal, obviously if the second object will have a bigger parachute, then it can build the drag enough so that it's going to faster, so that it's going to reach the ground better. You guys understand? That's another solution to the problem. But if both of them are given the same parachute, are given the same conditions, they were dumped from the same plane at the same height, well, in this case, the terminal velocity for the lighter object, for the less massive object, will be reached sooner than that of the more massive object that needs more time to build its terminal velocity, hence higher velocity to begin with. And since it's had more mass, so it's going to have definitely at the end more momentum to hit the ground with it, okay? We're going to discuss momentum later on, but that's basically something that is going to. So that's basically what I meant by terminal. Terminal velocity occurs when acceleration terminates. Then no more acceleration. When air resistance equals weight and net force is 0. Terminal velocity is same as terminal speed with direction implied going down. So that's the terminal velocity, terminal speed is the same thing because we're going down. So a skydiver in fall after jumping from a plane, that's a non-free fall. Weight and air resistance act on the falling object. As falling speed increases, air resistance on the diver builds up, net force is reduced because now more and more of the drag is coming into play, and that's compensating for the weight. So there is less and less acceleration, actually. Acceleration becomes less. When air resistance equals to the diver's weight, net force is 0 and acceleration terminates. Diver reaches terminal velocity, then continues the fall at constant speed. From that point on, he or she is not going to gain any more speeds, and that is the constant speed that's going to be with which is going to hit the ground. So when a 20 Newton falling object encounters a 5 Newton air resistance, its acceleration of fall is, of course, going to be less than g. As a matter of fact, we can find it, okay? The object is 20 Newtons in weight. So that means its mass is 20. It has to be mass times 10 equals to 20. So this mass must be 20 over 10, which is 2 kilograms. So this object is a 2 kilogram object. Now, when it's falling, okay, its weight is 20 Newton, but it's encountering a 5 Newton air resistance. So in this case, the net force is 20 minus 5, and 20 minus 5 is what? 15 Newton? Yes? Because 20 is in one way and 5 in the other way. So the net in this case is 15 Newton, correct? This is the kind of algebra you should be able to do. Did you say something, Marvin?
Oh, no, I was just agreeing that it is 15.
Okay. So it's 15 Newton. So how much acceleration 15 Newton will produce? 15 Newton will produce, let's use the acceleration formula. It's equal to the force, which is 15 Newton, divided by the mass of this object, which is 2 kilogram. And 15 divided by 2 kilogram is exactly 7.5 meters per second per second. And that is not g, because remember, g is exactly 10 meters per second per second. So this must be less than g. Okay?
I have a question.
Yes.
What does G stand for?
This is this is the gravity on Earth.
Oh, okay. Thank you.
All object on Earth fall with a value of g? In order to find the weight of an object, it's the mass of the object times g. It's just a fixed number, which is this one. 10. Does this make sense?
Yeah.
Yeah.
So
So
if
the
you calculate it,
so
Sorry?
the G is really, it's just a 9.8, but you're just rounding up to make it 10.
yes, you're right, Jacob. I mean, we use 10 because it's easier to multiply by 10 and divide by 10 than actually 9.8. If you ask me to divide something by 9.8, I have to put a calculator and do it.
Ah, gotcha. Thank you.
Okay, no problem. So Jacob's point is that, look, guys, I mean, I'm using 10, but that's actually an approximation of the real deal, which is 9.8. Okay, and you're absolutely right. So if a 50 Newton person is to fall at terminal speed, the air resistance needed it has to be exactly 50 Newton, but that's a bad example. Because that person is falling at terminal speed. That means the weight is 50 Newton and the speed is terminal. That means the acceleration is 0. If the acceleration is 0, the air resistance must be exactly what is needed to compensate for the weight of the person, and that is 50 Newton. The trouble why this is a bad example is because how much mass this object has. Well, 50 Newton divided by g, and g is 10 meter per second per second. So that's really the value of g. So this is, I want to find the mass of this object. 50 divided by 10 is what? What is 50 divided by 10? Come on, guys, wake up with me.
5.
5, very good. 5 kilograms. What person weighs 11 pounds? Because 5 kilograms is about 11 pounds. Which person weighs 11 pounds?
A baby?
So this must be a baby. Do not try this at home. Anywhere, not just at home, okay? Do not try, end of the story, okay? Because if you do, you're criminal. Not even for the sake of physics, this is allowed. So that's why I don't like this example in here. Okay, if it's a 500 Newton person, maybe, okay? And even that is probably a young man or a young woman, so you don't want to do that too, okay? As the skydiver falls faster and faster through the air resistance increases, of course. Because remember, the air resistance is proportional to the speed. Since it's falling faster and faster, that means the air resistance is increasing more and more, okay? As the skydiver continues to fall faster and faster through the air, the net force then is less and less. Because again, the weight never changes. So the weight is the same for this person, but this force now is becoming more and more. So the difference between these two is becoming less and less because this one, the weight, and this one is increasing. So in this case, it decreases. Okay. As the skydiver continues to fall faster and faster through her air acceleration also will decrease because the acceleration goes with the net force. If the net force was to decrease, as we argued earlier, then the acceleration must also decrease because the acceleration is given by the net force divided by the inertia of this person. Since this person is not basically losing weight or dropping a leg or an arm or something on the way, so the acceleration is not impacted by the mass. So the only thing that is impacting it is the net force. Since the net force is going less and less and less because you're building up more and more drag, then in this case situation, the acceleration will be also decreasing. And this is the example I gave earlier. Consider a heavy and a light person jumping together with same size parachutes from the same altitude. Who will reach the ground first? Ask yourself, which one has the higher speed? So there is a light person and there is a heavy person. This one will reach the terminal velocity soon. So his terminal velocity, for example, let's say for the sake of argument, is 50 meters per second. And this person will need more time to build up and reach. When this guy reaches 50 meters per second, this one is still building up more speed. So is going to run at, for example, at 70 meters per second. So which one will reach the ground first?
The
Lighter.
heavier person.
The lighter or the heavier? Look at the speed. Which one has higher speed? Which one is faster?
The heavier.
The heavier person definitely will reach the ground because he or she will gain more speed. So at the end, that's the terminal speed, whereas the other one is still basically cruising, coming at less and less speed. I mean, take it to the extremes, okay? Take it to a very, very light object, has reached terminal speed 1 meter per second, whereas this guy has reached 100 meters per second. Now, definitely the 100 meter, this is a lot heavier than the first one. So in this case, definitely the 100 meters per second is going to hit the ground. It's going to hit the ground hard. Okay. That's okay. All of these experiments are bad. Okay. All of these things are. Again, if we do the same experiment in vacuum, both objects will fall at free speed constant at the same speed, okay? Because there is no air drag. Both of them will have their mg. This is mg. This is mg. And since the mass is that's the weight divided by m, they will all fall with the same g. In vacuum, you will see this object fall exactly in the same point together at the same speed. But once you plug in, put in air, you will see the feather then build up more drag quickly than this coin. Probably there is not enough time for it to build the to reach its terminal speed and reach the ground, whereas this one will reach terminal speed faster because of its shape, because of the area, and because also of the air resistance in here with its sides in there. Okay. When the air is removed from a vacuum pump and the coin and feather activity is replaced, then in this case, the feather hits the bottom first before no. The coin hits the bottom first, no. Both the coin and the feather drop together at the same side by side. Correct answer is C. Okay. Now, when there is actually a vacuum, there is no air resistance because there is no, and both of them will reach the ground together. Okay, this is chapter 4. I think you guys are ready for the quiz. Please review the content of the chapters more in depth, okay? And I think you have 2 chances or 3 chances. I'm not sure exactly. Let me check the quiz again. You will have 3 tries, okay? The system will take your highest try. There are a lot of questions, so you have to be very careful, okay? So if you didn't do well in the first one, I recommend that you guys, let me stop the sharing the screen first, okay? So if you don't think that you did so well in the first try, please do not try immediately. Give yourself time, go back to the text, review these chapters again, and take the quiz again so that you score better the next time around. Chances are, again, because this is pulling from a data bank of different questions, that the next time around, they're not going to get the same questions. So don't count on it that you're going to get the same questions. So you have to understand basically what's going on, and so on and so forth. You have 36 questions and 45 minutes to complete these quizzes. And if you do well in the first one and score the highest point possible, then there is no need to take it again. That means you're in good shape. The discussion points today were 2 of them. You guys grab them? I really don't like to summarize things at the end because it's going to create a shortcut to things. Because people who are, who basically at the end don't attend classes really, they could come to the beginning or the end, and at the end, basically they didn't benefit in themselves. I know that they're not doing any harm to me or to you or anything like that. They're doing more harm to themselves. But out of fairness, because you guys are in here and sitting through this whole thing, and hopefully you're taking notes as I talked in the beginning. So So it's more fair to you guys than anything else who are doing the notes versus the people who. And I'm not saying that you guys are doing this, but I have noticed this also in the past in other classes where some people, what they do is they turn on their computers and they go somewhere else and then come later on and I'm asking them questions and they're not even participating, okay? Yeah, I think you guys are right. The ones in the discussion, I think you guys are right. Good. Does this answer the question that Jason asked?
Yeah, it does. Thank you.
Okay. So I guys see you guys Tuesday. I'm sorry. What am I saying Thursday for? We are Thursday already. Let me stop the recording first.